Hello. Today we're going to talk about Chapter 19, Testing Hypothesis about Proportions. Okay, so why would we do a hypothesis test? So in this example, we have a company produces parts and they have a failure rate of 20%. In an attempt to improve this rate, the manufacturers have introduced new procedures. So since those started, 400 parts have been produced and the failure rate for those is 17%. Has the failure rate really decreased, or is that just luck? All right. This is when we would use a hypothesis test. Okay. We assume that P has a certain value, and we use the normal model to compare this value to our observed. Okay. So we determine the probability of getting this observed data, and if that probability is low, then we have evidence that our hypothesis is false. If it's not low, okay, we have no evidence that it's false. Because if the probability is really low, that means it's very unlikely, right? Think of it like that. Okay, so then our hypothesis would be false. Okay, what is an hypothesis? We are working with models that we adopt temporarily. We start with two kinds of hypotheses. You have the null hypothesis, which is denoted by HO, or like a 0. Then that specifies a population model parameter of interest. Okay, it's usually written like this. So when it's written HO, that is the null hypothesis, and you would say P, the parameter, is equal to whatever the hypothesis value is. The alternative is what you were testing for. You're trying to find and see what that is, what probability of that is. So we denote this by HA. Okay, so that's the alternative hypothesis. So that's what we consider plausible if we reject the null. We want to compare our data to what we would expect given that the null hypothesis is true. Okay. We do that by figuring out how many standard deviations away from our proposed value is. Okay, so how far apart they are, and then that'll find our probability, right, using the normal model. Okay, think of it like a jury and trials. So to prove someone is guilty, we start by assuming they're innocent. Okay, we're not getting into, well, sometimes that's not how it's done. No, we're not getting into that. But this is how jury and trials, how the law should be done. Okay, if you want to debate that, go into like psychology. All right. So here you want to retain the hypothesis. You retain that hypothesis until it is unlikely beyond a reasonable doubt. Okay. On the jury, you don't want to be on that jury that sends someone to jail that didn't do the crime. Okay, that's awful. So, without a reasonable doubt, that's when you say that they're guilty. Okay? Same logic for statistical tests. We begin by assuming that the hypothesis is true. We'll consider whether the data is consistent with that hypothesis. If it is, all right, if the probability is fine, all right, then it's just like that, just like a jury. We ask whether they are not. I can't find my words. So if our data is consistent with the hypothesis, then we can then all we can do is retain that hypothesis. So it's true. If it's not, then like a jury, we ask whether it's not without a reasonable doubt. And what's great about statistics is that you can quantify that level of doubt. All right? We can use that model proposed by our hypothesis to calculate the probability. All right? Now, based on that probability, or that p-value, All right, if the p-value is high, then we can't reject the null hypothesis, the original. All right, if the p-value is low, we'll reject the null hypothesis and go with our alternative. It's very important that you say it these two ways. It's either you fail to reject it or you reject the null hypothesis. All right, so why would we do that? Okay, think about an innocent defendant. Okay, someone who is innocent. If the evidence is not strong enough to reject the presumption of innocence, the jury returns with a verdict of not guilty. The jury doesn't say that he's innocent. Okay, there's just not enough information to prove guilt. Okay, that's why we don't say we accept it, we agree with it, we approve, this is it. No, we say we fail to reject it. Well, you know what? This looks to be right, based on the evidence, right? That's what statistics does. Okay, it's never having to say you're certain. All right. So obviously in a trial, the burden of proof is on the prosecution. So in a hypothesis, the hypothesis test, the burden of proof is on the unusual claim, the alternative hypothesis. Okay. All right, so let's do an example. So a research team wants to know if aspirin helps to thin the blood. The null hypothesis says it doesn't. They test 12 patients. They test 12 patients testing for thinner blood and get a p-value of 0.32. They proclaim that aspirin doesn't work. What would you say? Nope, you cannot conclude that. All right, you can't say it causes it, or you're not proving it. You can only conclude that the experiment was unable to reject the null hypothesis. On the basis of 12 patients, based on this, we were unable to show the aspirin was effective. Okay? You don't say the other way, right? Don't say with certainty. Okay? An allergy drug gives relief to 75% of the patients. All right, they want to know if that new formula works better. What should the null hypothesis be, the original hypothesis? So you write it as HO, and then P equals 0.75. The new drug is tested, and the p-value is 0.0001. All right, well, think about what that is as a percentage. Okay, that's not even close to 1%. So, very, very strong evidence against the null hypothesis. That is very unlikely. So, we can reject the null hypothesis and conclude that the improved version of the drug gives relief to a higher proportion of patients. Okay, so I'm trying to get you to understand what a hypothesis test is. Okay, and then we'll get into the mechanics of it. Which brings us to the mechanics. There are 4 basic parts to a hypothesis test. You have your hypothesis, your model, mechanics, conclusion. All right, let's break them off one by bit. Or one by one, whatever. So step number 1 is the hypothesis. So you have the null hypothesis. Okay, so it translates our question of interest into parameters. And then you have your alternative hypothesis. Again, it's better with examples, so here, let's look at this one. DMV claimed that 80% of candidates pass driving tests, but a survey of 90 randomly selected teens found only 68 who had passed. So, does it suggest that the passing rate for teens is lower than the DMV reported? So, our null hypothesis would be the P equaling 80, or I'm sorry, 0.8, 80%. All right, because that is the population parameter. That's what they're claiming is true. The alternative hypothesis is where the P is less than 0.8. You see where I got less than from? Oh, right there. Lower than. Okay. Is it lower than what we expect? So that's how we write it. So pretty much the alternative hypothesis looks very similar to the null hypothesis. It's just the expression turns, or the equation turns to an inequality. So the second part, excuse me. So after we label our hypotheses, we do our model. So then we always have assumptions that we have to check first. Okay, I'm sorry. We have to state the assumptions and check the conditions. So we always should end it with some kind of statement. Because of the conditions are satisfied, I can model the sampling distribution. Okay, that's how you should always write it when you do a free response question. All right, it might be the case that because the conditions are not satisfied, you can't proceed with the test. That sometimes happens. All right, don't be alarmed. All right, it's not like it happens all the time, but I've seen an AP exam question where it stops there. Okay. So each test we've discussed has a name that should be in your report. Okay, so keep track of the tests that we're doing. So the first one we'll do, well, not just the first one, we've done lots of these things, is the 1 proportion Z test. Okay, so conditions for the 1 proportion Z test are the same as the 1 proportion Z interval. We're testing this hypothesis, and we have, this is our Z score, and this is our standard deviation. All right, when these conditions are met and the null hypothesis is true, the statistics follows a normal model to obtain the p-value. Okay, so if we have our conditions met, we can use these things to follow a normal model and get the p-value, the probability. All right, let's do an example. The DMV claimed that 80% of candidates passed driving tests, but a survey of 90 randomly selected teens found only 61 who had passed. So this is how we would check for the conditions. All right, the first condition we can check is for randomness. Well, that's pretty easy to do because the 90 teens surveyed were a random sample, randomly selected teens. Okay, 10%, well, it was 90 kids, so 90 is fewer than 10% of teenagers who take a test in a large city. Okay. Oh, I think part of the question was cut out. Okay. So either way, in most cities, 90 is going to be less than 10% of all the teenagers. Your success failure rate would be this. So we do the number of people, trials, whatever, times the probability of success. Then the number of people, trials, whatever, times probability of failure, right? Think of it like that. Here, both of those numbers, 72 and 18, are greater than 10. There. Now that we have all three things shown, what can we conclude? Conditions are satisfied, so it's okay to use a normal model and perform a 1 proportion Z test. Okay, so this is how we show we did our conditions. Let's see, what's the p-value? We haven't gotten here yet. You can use your calculator. You can do it by hand. It's easier to do with examples. Let me get through the nitty-gritty first. All right, now the third part of your hypothesis test is the mechanics. So again, just like I said, the actual calculation is from the data. So you have different tests that you can use with your calculator or different formulas. Either way, it's good to know the formulas. You want to make sure you understand which test you're doing too. All right, the ultimate goal of the calculation is to obtain a p-value. The p-value is the probability that the observed statistic value could occur if the null model were correct. So what's the likelihood of getting that sample? If it's small enough, we'll reject the null hypothesis because there's no way that's true, right? What's the odds of getting something that crazy? All right, if the p-value is a conditional probability, it's the probability that the observed results could have happened if the null hypothesis is true. Okay. And the fourth and final part of the hypothesis test is your conclusion. It's your final statement. You need to put this in there. You either need to say we reject or you fail to reject. All right, and always the conclusion should be stated in context. Okay, don't make it all super mathy. Okay, make it, oh, you got to put that stuff in there too, but you want to make sure you put the sentence in there. All right, let's see. Okay, so there are three possible alternative hypotheses, whatever. The first one is you can have a two-sided alternative. All right, that's when you say that the parameter isn't equal to it. So it doesn't matter if it's greater than or less than. Okay, so it's two-sided because we're interested in either side of the null hypothesis. So visually, you know, if you imagined your normal curve, okay, you would say it doesn't equal that, so it can either go to the left or to the right by a certain standard deviations, right? It can be 2 standard deviations higher or 2 standard deviations lower. All right, the other type of alternative hypotheses are one-sided. All right, so that's only going in one direction. So visually, it would look like this. If it was greater than, you're doing the right side. If it's less than, you're doing the left side. And also think about what your z-scores would be. All right, your z-scores would also be negative for this one and positive for greater than. Okay, so big question. How small should the p-value be in order for you to reject the null hypothesis? Well, guess what? It really depends, okay? It depends on our context, what's going on, okay? The importance of the issue is also being tested. So like, think for example, when screening for a disease, you want to treat all those who are sick. So you might get away with a p-value being 0.1 or 10%, okay? But something that's, you know, really strongly believed, like the earth is round, okay, you're going to need a very, very strong data, a very, very small p-value to reject that, okay? We're ignoring flat earth theory, okay? It is, the earth is round or oval, whatever. So your conclusion about your conclusion should be accompanied by the p-value of the test. So you should always put that p-value in there. All right? Even better, put in that confidence interval. All right? Don't just declare that the null hypothesis is rejected or not rejected and then you're done. No, you gotta tell the p-value, and this, you know, you can make your own decisions, but that p-value can also help readers make their choice. Because if it's right on the cusp of, you know, I don't know if this is going to affect you or not. All right, leave it up to the readers. So throw that p-value in there. It's better to have it. All right, so let's get down to the nitty-gritty. Let's do some examples. All right, I'm going to walk you through a whole bunch of them. So take a minute, pause it, read it, learn what's going on. All right, so I'm going to just show you everything and then walk you through what I did. I know, it's a lot. Start with the red. So in red over here, oh, I'm sorry. I didn't think about colorblind. Okay, so here, I'll get my pen. All right, so right here, okay, we're going to state our null hypothesis and our alternative hypothesis. So notice I used the greater than because in my question I said higher than. Because of that question, I use greater than. All right, now we test the conditions, or check the conditions. So random, we're assuming inspecting 400 random homes. Okay, that seems reasonable. That's this one right here. All right, next one, the 10% condition. Well, 400 homes has got to be less than 10% of all U.S. homes. All right, think about it. Rickards has 1,600 students. Yeah, I think there's more than, that's less than 10% of all U.S. homes. All right, then we check the success failure. So that's the number of trials, events, whatever, people, things, times probability of success. So 0.9, your parameter there. Then Q would be the 1 minus the parameter, so 0.1. And both of these values are greater than 10. So let me go ahead and write that. Greater than 10. Awesome. Once I have that, all right, then I can go ahead and find my mean. All right, I have that already, so I'm going to write that out. My standard deviation. All right, using your formulas. All right, remember, go back to page 10. Okay, page 10, your formulas. So here we can get our standard deviation. Then we can get our z-score. We plug that in. And then we can use our normal PDF. Okay, think about what your z-score is. In case you forgot, if you graph it, we're doing a normal curve. So the mean here would be 0, and the standard deviation would be 1. I know, I did, whatever, those are just the, anyway. So then here, yeah, I should have used that value. So then, I'm sorry, the z-score is 2.6. So while the mean is here, we want to be greater than that. So we're going to be over here and do the greater than. So this is at a z-score of 2.6. So what's that probability? It's going to be very low because it's almost 3 standard deviations. Okay, let me get out the calculator. Okay, so to use your normal PDF, we go to second vars. Yes, perfect. Enter. All right. Our x value is 2.666666, right? What is that? 2 2/3, 8/3. So I'm going to put 8 divided by 3. I just like being exact. Our mean is 0. Our standard deviation is 1. See, I knew I should fix that. All right. Then our p-value oh, sorry. I was reading that value and I was like, how did I not get 2.6? Just kidding. The p-value is 0.0114. Notice I had a round there. That's how we can get our p-value. All right, using our formulas. All right, let's try another example. So here we're dealing with orange M&Ms. All right, why don't you pause it, give it a whirl. Here we start with our null hypothesis, right? That's what it's supposed to be. Our alternative hypothesis is we just want to know if it contradicts this. So is it just not 0.2? All right, randomness. Each bag is random. You have 122 M&Ms has got to be less than 10% of all M&Ms because I'm pretty sure I've eaten more than, yeah, a lot more of those M&Ms than that. So success, failure. So you do those formulas. Both are greater than 10. Perfect. We satisfied our conditions, so we can continue using a 1 proportion z-test. So we have our formulas. We have our graph if we want to visualize it. So then we can just plug this into our calculator using a normal PDF. All right. If you're lost, just holler at me in class and I'll be happy to talk to you one-on-one. Okay, let's try example 3. So why don't you pause this, read this, get used to the question. Okay, our parameter of interest and the null and alternative hypotheses. So, the parameter of interest is the percentage of delinquent customers, okay, who haven't been paying their bills, okay, past due. Our null hypothesis is when it's equal to 0.3. That's what they're saying it is. Alternative hypothesis is they want to know if this is effective, so it has to be greater than. Okay, pay attention to the words. I know. So after completing a test run, they calculate a p-value of 0.003. What does that suggest? Well, that's a very, very low p-value. It's not even 0.5%. So that leads us to reject the null, stating that it is more effective in getting people to start paying their debts. So that doesn't really follow our normal parameters, so that has to be different, so it must be doing well. Okay. The statistician at the bank says the results are clear and they should switch to the DVD method. Do you agree? All right. Even though there is strong evidence, all right, we don't know how much higher than 30% the new proportion is. We'd like to see a confidence interval to see if the new method is worth the cost, right? What if you're at the high end of that interval? Okay. What if that interval has a large spread? Think about it further than that, right? It's easy to want to jump to conclusions, all right? But again, statistics is all about statistics is about never having to say you're certain. Sorry, it's just a play on. I just love that pun. It's just great. In case you're wondering, that's an old line. Love means never having to say you're sorry, from an old movie. All right. Example number 26 in the book. How surprising. Another example. But aren't you burnt out of doing it by hand, right? It's kind of not fun to keep doing the formula over and over again. So why don't we do the calculator this time? Okay, we're going to run a 1 proportion z test with our calculator. So first, make sure you do all the other beginning stuff. Your null hypothesis, alternative hypothesis, list your conditions, state your conditions. All right, so now we're going to use the 1 proportion z test. So we go to statistics. Let's see. Tests. Yes, that makes sense because it's a test. So we go down to number 5 on my calculator. So 1 proportion z test. Notice how it's written PO. All right, your parameter is 0.92. Then our X is, let's see, we had 171, think of it as successes out of 200 trials, and we want to do less than. So make sure you highlight the correct one and calculate. So we get our z-score and you get your p-value. Notice the z-score is more than 3 standard deviations. So notice that that p-value can't be 3.5. Notice this on the end, it's a lot smaller. So, see, notice how I wrote it down here. Okay, so because the p-value is very low, we have to reject the null hypothesis. So we don't just state it like that. All right, that's too mathy. You got to put it in words that people can understand. Okay, that's what statisticians do. They translate the math into normal language. Okay, so the next thing you would say is there is strong evidence that these seeds have lost viability. Their germination rate seems to be less than 92%, so it's not following the parameter. Okay. All right, I'm going to keep doing examples. All right, this one, let's do it with a calculator. Okay, so is this death rate unusually high among the movie crew? You should have paused it, tried this on your own, right? No one's going to see you mess up. Okay, so here's your hypotheses. Here's your conditions met. So yes, all right, assuming the sample to be a typical group of people, we run our one proportion z-test and got a p-value of 0.008. So again, make sure you add the information for your one proportion z-test. I don't know why I don't have that written there. Probably to add this. Okay. Does this prove that exposure to radiation increases the risk of cancer? Does this prove? Right away, you should know the answer. No. No. We don't prove anything. Okay? We don't prove it. So, this group may be atypical for reasons that may not have anything to do with radiation. We don't know. All right? We don't know everything. All right? Got to be open. All right, let's do another example. So here we want to find the standard deviations. Pause it, read it. Okay. So here I would use your calculator. I would go to your one proportion z-test. And here the College Board is reporting 60.3. What am I doing? Put that decimal in the right spot. 0.603. And here, the teacher got 34 out of 54 students. And she believes they're typical students, so that it satisfies all those things. Make sure you go through that before you just run into a one proportion z-test. Like, for example, 60.3 times 54 is more than 10, and 39.7% times 54 is also more than 10. Okay, so we had random students that were typical of an AP course, and what else? Oh, 54 has got to be less than 10% of all the teacher or all the kids that took AP stats. Okay, so we satisfied our conditions. So let's see. We want to know, obviously that's more, so we're going to use greater than and calculate. So notice what the z-score is, 0.399999, so you got to round up, so that becomes 0.400, and the p-value is 0.34. So we learned two really important pieces of information there. Well, the z-score can tell us, okay, that it is far less than one standard deviation above the mean. Far less. Oh, yeah, because it's 0.4. Silly me. I'm trying to like round up like a percentage. All right, so this is far less than one standard deviation, so it's very close to the mean. All right. Now, can she claim that her school is different? Since the p-value is so high, no. All right, it's pretty likely to get something like that, or a sample of her size. So no, that's not a big deal. It's great. Be happy. All right, but it's not significantly different than the normal population. Okay, so here's all the things, that can go wrong. So be careful. Okay. Their hypothesis tests are widely used and therefore misused. Okay. Statistics is, again, the number one type of math that is misconstrued to fit people's agenda. So, or they just don't understand. Okay. People don't understand what the data is implying, and they say that they're confident that it proves something. No, that's not what statistics does. Okay. First of all, you need to get your null and your alternative hypothesis before you collect your data. You don't just start looking at your data and then make assumptions on what you already know. No. Okay. Let's see. we don't make our null hypothesis what we want to show. Okay, and we can only reject the null hypothesis. Again, just make sure you always check your conditions. I think I hit that enough. All right. If you fail to reject the null hypothesis, don't think a bigger sample would be more likely to lead to rejection. Each sample is different, and a larger sample doesn't mean it'll duplicate your current observations. Okay, so just getting a different sample is good enough. Okay, not necessarily larger will always prove something. All right, and here's a summary of what we learned. Hopefully this wraps everything up. If you have any questions, please feel free to come ask me anytime.